Let us look at an equation f dash of z, which is the derivative of an analytic function f of z. Whenever f has a representation, f of z equals u of xy plus I times v of xy, we have the derivative of analytic function f of z given by f dash of z equals dou u by dou x plus I times dou v by dou x. Let us look at the proof for the equation. We know the Taylor's theorem applicable for one variable function given by f of x plus h equals f of x plus h times f dash of x plus h square by 2 factorial times f double dash of x plus etc. plus h raised to n divided by n factorial into nth order derivative of function f of x. We know that h is the small increment given to variable x, and we wish to find out the value of function f at the incremented position x plus h. If we extend the concept of Taylor's theorem for function of two variables, that is, the function now involves two dimensions x and y. If we give small increments to both the variables x and y, say we wish to find out the value of f of xy at positions x plus h and y plus k. By Taylor's theorem for function on two variables, we have f of x plus h comma y plus k given by f of xy plus h times f dash of x plus k times f dash of y plus h square by 2 factorial times f double dash of x plus k square by 2 factorial times f double dash of y plus etc. Here, if h and k are very small quantities, we can even neglect the terms h square and k square. That is, the terms involving h square and k square can be neglected if it is given that h and k are very small increments. Recall that the derivative of analytic function f of z is given by f dash of z equals limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z, where delta z is the small increment given to the variable z. So here, in order to find out the derivative of dash of z, we will have to find out f of z plus delta z. To evaluate the expression of f of z plus delta z, we may make use of Taylor's theorem on function of two variables. We know that z equals to x plus iy. So f of z will surely be a function on two variables x and y. So we have f of z plus delta z given by u of x plus delta x comma y plus delta y plus I times v of x plus delta x comma y plus delta y. If we apply Taylor's theorem to both functions u and v, where u and v are functions on two variables x and y, we have Taylor's theorem applied on u, where u is a function of two variables given by u of x plus delta x comma y plus delta y becomes u of xy plus dou u by dou x delta x plus dou u by dou y into delta y. Here we have neglected the higher powers of delta x starting from the second order power, because delta x and delta y are considered as very small increments, and hence their square terms will be even more negligible. Similarly, when we apply the Taylor's theorem for functions on two variables for the function v of x plus delta x comma y plus delta y, we have v of x plus delta x comma y plus delta y given by v of xy plus dou v by dou x delta x plus dou v by dou y delta y. That is, to evaluate f of z plus delta z, we applied Taylor's theorem on two variables to both the functions u and v separately. Now we can group the terms. We grouped terms of f of z plus delta z such a way that terms involving delta x is grouped, terms involving delta y is grouped, and term independent of delta x and delta y is grouped. We thus obtain term independent of delta x delta y as u of xy plus I times v of xy. When we grouped term containing delta x, we obtained dou u by dou x plus I times dou v by dou x. When we grouped term containing only delta y, we obtained dou u by dou y plus I times dou v by dou y. U of xy plus I times v of xy can be rewritten as f of z. If we take f of z to the LHS, we have f of z plus delta z minus f of z equals ux plus I times vx into delta x plus uy plus I times vy into delta y. Since we have assumed that f is an analytic function, CR equations hold here. So we can replace uy appearing here by minus vx and vy appearing here by ux. We wish to get all the partial derivatives in terms of x. Here we express the RHS using expressions which are partial derivatives expressed in terms of x, and for that we make use of CR equations. Applying CR equations, we have f of z plus delta z minus f of z given by ux plus I times vx into delta x plus minus vx plus I times ux into delta y. We have, note that all the partial derivatives in RHS are expressed in terms of partial derivatives of x. We can replace minus 1 by I square. So we have ux plus I vx delta x plus I square vx plus I times dou u by dou x into delta y. We can take outside I common. Thus we get ux plus I vx into delta x plus I times delta y, because in these two terms we are having common factors ux plus I vx. We can replace delta x plus I times delta y by delta z, because we have z equals x plus iy. Therefore, small increment delta z can be given by delta z equals delta x plus I times delta y. If we bring delta z as the denominator in the LHS, we obtain f of z plus delta xz minus f of x minus f of z divided by delta z equals ux plus I vx. To get the desired limit f dash of z, we apply limit delta z tends to 0 to f of z plus delta z minus f of z divided by delta z, which is equal to ux plus I vx. Thus, whenever f of z is an analytic function, we have f dash of z equals ux plus I times vx.